Welcome to another related rates problem. Two identical 12-inch rulers on a desk form an isosceles triangle with included angle theta. If Mickey moves the rulers so that theta increases at a rate of 2.5 radians per second, what's the rate of change in the area of the triangle when theta equals pi-4s? Let's draw a picture. A picture will make it easier for us. So he's moving these rulers around. He's opening them and closing them. That's a good enough picture. They're supposed to be the same, but so they're two. I guess I could make it look a little bit more the same. All right, there we go. So two identical rulers, opening and closing them, and so he's making a triangle with them, right? Of course, they would be an isosceles triangle because each of the rulers is 12 inches. This is theta right there, right? That's that angle in between the two rulers, right? The angle created by the two rulers. And so we want to find the rate of change in the area of the triangle when theta is pi-4s. So let's identify all the variables in the problem. All right, so we have a triangle, right? And so A and B are sides in the triangle. So one's A, one's B. They're exactly the same, but in terms of the length, theta is the angle created by the rulers. All right, and so we are looking for the rate of change in the area of the triangle. Identify which, if any, of the variables in the problem will remain constant. Well, theta will change as the rulers are moved around, and that's going to change the area of the triangle. What will not change is A and B. A is 12 inches and B is 12 inches. Right? They are going to stay that way. They are rulers. We are not chopping off a piece of the ruler. They are just going to stay the exact same length they are. Identify the rates that are given and the rate you wish to find. Right? So we are given d theta dt. Right? So theta increases at a rate of 2.5. So d theta dt is 2.5 radians per second. We want, so squeeze it in there. I'll put it over here, I guess. dA dt. That's what we're looking for, right? The rate of change in the area. All right, so I have a formula for you, which is why I chose the sides to be called A and B, and this is called Heron's formula. It's a very handy formula because it lets you find the area of a triangle. And so normally when you find, remember back to geometry, when you find an area of a triangle, right, you needed base and base and height had to be perpendicular to one another. No worries about that with Heron's formula. All you need is two sides and an included angle. Side, angle, side. If you have two sides and an included angle, you don't even care what the altitude of the triangle is because you don't need it. Area will be 1/2, just like 1/2 base times height, times A and A times B, and A and B are just the two sides, and sine C is the angle between. And if you look at our diagram, that's exactly what we have: A, B, and we have the angle, if I can move it up, angle in between those two. All right, so we can use Heron's formula. Make sure you remember it or write it down so that you can use that whenever you need it. So that is going to be the equation that we are going to take the derivative of. That's the formula that we're working with. But first, so you might be thinking, oh, we've got to use the product rule here. But no, because A and B are constant. So we need to, first of all, before we do anything else, we need to plug in those values that are constant throughout the problem. All right, so over here. We'll write those in. So we have A equals 1/2 and then 12 times 12 sine C. All right, now we have our equation, but we should probably simplify that. So that's going to be half of 144 would be 72. So A equals 72 sine C. There's our equation. Let's take the derivative of our simplified equation. So implicitly differentiate both sides of the equation with respect to time. All right, so this was 4, by the way, Heron's formula, and this is 5. All right, so we have dA dt. All right, so the derivative of sine is cosine. So 72 cosine, oh, sorry, not C, theta. That's right, C is not our variable. Theta is our variable. So this would be 72 cosine theta d theta dt. Now we just need to plug in because we have dA dt isolated. All right, so theta is pi fourths, I do believe. Yep. So theta is pi fourths. This might be a good place to write it because we're interested at the moment that angle is pi fourths. So we have dA dt equals, so this would be 72 cosine pi fourths, and this was 2.5 radians. All right, so let's evaluate cosine. Pi fourths is right here, literally splitting that box in half. All right, this is a 45, 45, 90 triangle, or pi fourths, pi halves. Opposite is 1, adjacent is 1, hypotenuse is the square root of 2. All right, so cosine is adjacent over hypotenuse, so cosine pi fourths would be 1 over the square root of 2, or when we rationalize it, square root of 2 over 2. So now we'll replace cosine pi fourths with square root of 2 over 2. So we have dA dt equals 72 times the square root of 2 over 2. And I'm going to change that 2.5 to 5 halves, just because that'll be easier to simplify. All right, and so now all we got to do is simplify. All right, so let's see, we can cancel out those 2's. So 72 divided, I think, yes, we can divide by 4. 72 divided by 4 is going to be 18. Yes, 18. So we have 18 times 5, that's going to be 90 square roots of 2. And the unit of measure is radians, no, excuse me, not radians. This is area, and this was in inches, because these were 12-inch rulers. Inches squared per second. There you go. So the area of the triangle is increasing at a rate of 90 square roots of 2 inches squared per second when theta equals pi fourths. And there we go. That's all there is to it. We're done. All right? So if you have any questions, let me know. Otherwise, another problem solved. We've done all of these in less than 10 minutes. That's pretty good for a multi-step problem. So I'll see you in the next problem. Bye for now.